This is lesson 1.6 or 3.5 out of your textbook, limits at infinity. So here we have horizontal asymptotes. You can see the definition of a limit at infinity. Let L be a real number. The statement, the limit as x approaches infinity of f of x equals L, means that for each epsilon greater than 0, there exists an m greater than 0, such that the absolute value of f of x minus L is less than epsilon whenever x is greater than m. What that means is the further right I go, the closer to this value L I get, without actually touching it. The statement, the limit as x approaches negative infinity of f of x equals L, means that for every epsilon greater than 0, there exists an n less than 0, such that the absolute value of f of x minus L is less than epsilon whenever x is less than n. That just means the further left I go, the closer I get to that value L without actually touching it. This means that no matter what, I stay within epsilon above or below this actual limit. I can go back and forth as many times, but I'm getting closer and closer and closer to it. So horizontal asymptotes, the definition is that the line y equals L is a horizontal asymptote of the graph when the limit as x approaches negative infinity of f of x equals L, or the limit as x approaches positive infinity of f of x equals L. Certain properties still hold true. You can add or subtract two limits together. You can multiply two limits together as well. And theorem 3.10, limits at infinity. If r is a positive rational number and c is any real number, then the limit as x approaches infinity of c over x to the r power equals 0. What that means is that a number divided by infinity to any power equals 0. Same thing, a number divided by negative infinity is also going to give you 0. So for our examples, we are going to find the limit as x approaches infinity. Well, I can separate this out into the limit as x approaches infinity of 5 minus the limit as x approaches infinity of 2 over x squared. Well, the limit as x approaches infinity of 5 is 5. The second part is 2 over infinity. 2 over infinity is 0. And 5 minus 0 means the limit is 5, which means that function had a horizontal asymptote of 5. All right, for this next one, it's not quite so simple. I can't just break it apart like that. The trick here is to divide everything, oops, you can't see that, sorry, everything by the highest power of x in the denominator. That is the trick that'll save you on these limits at infinity. So since I can't do anything with this right away, I divide every single thing by x. So I have the limit as x approaches infinity of 2x divided by x minus 1 divided by x over x divided by x plus 1 divided by x. Now this looks really terrible, but I simplify a little. Because I know 2x over x is just 2. 1 over x can't simplify. X over x is 1. 1 over x cannot simplify. But now when I plug in infinity, well, 2 stays 2. 1 over x becomes 0 because 1 over infinity is 0. Over, my 1 stays a 1. 1 over x becomes 0 again. So I get 2 over 1, or just 2 for my limit. So let's try a few more. There we go. So the trick for these, remember, divide everything by the highest power of x in the denominator. So I'm going to divide everything by x squared in this one. So I have the limit as x approaches infinity of 2x over x squared plus 5 over x squared over 3x squared over x squared plus 1 over x squared. That becomes the limit as x approaches infinity of 2 over x plus 5 over x squared over 3 plus 1 over x squared. Now anything that still has an x in the denominator will go to 0. So I'll have 0 plus 0 over 3 plus 0, which is 0 over 3, or just 0 for my limit. For the second limit here, we do the same type of thing. We're going to divide everything by the highest power of x in the denominator, which is again x squared. So I'll have the limit as x approaches infinity of 2x squared divided by x squared plus 5 divided by x squared over 3x squared divided by x squared plus 1 over x squared. Simplify that a little bit. The limit as x approaches infinity of 2 plus 5 over x squared over 3 plus 1 over x squared. And that'll give me 2 plus 0 over 3 plus 0, which gives me a final limit of just 2/3. And for the third one here, we do the same thing. Divide everything by the highest power of x in the denominator. So I take the limit as x approaches infinity of 2x cubed over x squared plus 5 over x squared over 3x squared over x squared plus 1 over x squared. Simplify this out. The limit as x approaches infinity of 2x plus 5 over x squared over 3 plus 1 over x squared. Now as x goes to infinity, 2 times infinity happens, plus a 0 because there's an x in the denominator, over 3 plus 0. Well, infinity over 3 is still infinity. That limit still does not exist because it still goes to infinity. Some guidelines here for finding our limits. These are the same as the guidelines for finding horizontal asymptotes that we learned in pre-calc last year. If the degree of the numerator is less than the degree of the denominator, the limit is 0. If the degree of the numerator is equal to the degree of the denominator, then the limit is the ratio of the leading coefficients. And if the limit of the numerator is greater than the degree of the denominator, then the limit does not exist. It'll go to positive or negative infinity. So let's try this one now. On this one, we can't use the shortcut because they're different. The degree of the numerator is 1. The degree of the denominator is also technically 1 because it's the square root of an x squared. So we're actually going to divide everything by the square root of x squared, because I want to get the biggest exponent in the denominator out of there. So I'll take the limit as x approaches infinity. The square root of x squared, remember, is just x though. So in the numerator, I can do 3x over x minus 2 over x. In the denominator, I'm inside of a square root, so I'm going to just do an x squared because it's already got the square root given to me there. So this gives me the limit as x approaches infinity of 3 minus 2 over x over the square root of 2 plus 1 over x squared. Now I do my infinity part. So my numerator becomes 3 minus 0 over the square root of 2 plus 0, which is 3 over the square root of 2. We still have to rationalize that. Square root of 2, square root of 2. Our limit is 3 square root of 2 over 2. For the second one here, notice it's the same thing except that I'm approaching negative infinity. Well, in the numerator, I'm going to divide by x because in the denominator, I'm dividing by the square root of x squared. But the problem here is that the square root of x squared is definitely positive. This just x value, though, could be positive or negative. And as I go towards negative infinity, it's definitely negative. So I want to make sure that this is actually going to be a negative, so I stick a negative in there. The only difference this makes is that in the numerator, everything stays the same. In the denominator, I stick an extra negative out front. So I have the limit as x approaches negative infinity of 3 minus 2 over x over negative square root of 2 plus 1 over x squared. So I get 3 minus 0 over negative square root of 2 plus 0, which is 3 over negative square root of 2. So the only difference here, we get the same exact answer, except that we will have a negative in the front compared to that last problem. All right, so the limit as x approaches infinity of sine of x. Well, if you think of sine of x, remember that it oscillates back and forth forever between positive 1 and negative 1. So this limit does not exist. And we'll say why? Because it oscillates between y equals negative 1 and y equals positive 1. Now the limit as x approaches infinity of sine of x over x. Think of these limits separately. The limit as x approaches infinity of sine of x over the limit as x approaches infinity of x. Well, that denominator, that limit is infinity. The numerator is just going to be somewhere between negative 1 and 1. So that's just going to be some number all the time. And a number divided by infinity is always 0. So that limit actually equals 0. All right, so let f of t measure the level of oxygen in a pond, where f of t equals 1 is the normal unpolluted level, and the time t is measured in weeks. When t equals 0, organic waste is dumped into the pond, and as the waste material oxidizes, the level of oxygen in the pond is given by f of t. What percent of the normal level of oxygen exists in the pond after 1 week, 2 weeks, 10 weeks, and the limit as t approaches infinity? So we're just going to do some plug and chug. I need f of 1, which is 1 squared minus 1 plus 1 over 1 squared plus 1, which is 1 over 2, 1/2, or 50%. F of 2 is 2 squared minus 2 plus 1 over 2 squared plus 1, which is 3 over 5, which is 60%. F of 10 is 10 squared minus 10 plus 1 over 10 squared plus 1, which is 91 over 101, which is 90.1%. And then we want the limit as x or t approaches infinity of f of t. Well, the trick for a rational function is to divide everything by the highest power of the variable in the denominator. So I'm going to divide everything by t squared. So I have t squared over t squared minus t over t squared plus 1 over t squared, all divided by t squared over t squared plus 1 over t squared. Oops, sorry, I forgot my limit as t approaches infinity. There we go. So that's the limit as t approaches infinity of 1 minus 1 over t plus 1 over t squared over 1 plus 1 over t squared. The limit as t approaches infinity then is 1 minus 0 plus 0 over 1 plus 0, which is just 1, or 100%. So that means eventually our pond will basically be back to 100% oxidization. All right, definition of infinite limits at infinity. F is a function defined on the interval a to infinity. The statement, the limit as x approaches infinity of f of x equals infinity, means that for each positive number m, there's a corresponding number n greater than 0, such that f of x is greater than m whenever x is greater than n. That just means that as my x values get bigger, my y values also get bigger. And same thing for the negative end. As my x values get bigger, my y values just continue to get smaller. Similar definitions for the other side, except these are as x gets smaller. So the limit as x approaches infinity of x cubed. Well, infinity cubed is still infinity. That limit does not exist, but it goes to infinity. For b, negative, as x approaches negative infinity, we have negative infinity cubed, which is still negative infinity. Those are infinite limits at infinity. And for this last one, the limit as x approaches infinity. Sorry, these last two. To do this, we want to use our same trick as before, divide everything by the largest power of x in the denominator. So the limit as x approaches infinity of 2x squared over x minus 4x over x, all over x plus 1 over x. So that'll be the limit as x approaches infinity of 2x minus 4 over 1 plus 1 over x. When I plug in infinity, I have 2 times infinity minus 4 over 1 plus 0. Well, a number times infinity is still infinity. And infinity minus a number is still infinity. And infinity divided by a number is still infinity. So that one is infinity. Next one is the same thing except as x approaches negative infinity. So we would get to the same exact last step and plug it in. So 2 times negative infinity minus 4 over 1 plus 0. Well, this just makes negative infinity. Minus 4 is still negative infinity. This one just goes to negative infinity then. Now you will try some.